You could make the argument that Heisenberg himself got it slightly awry. That's where the real weirdness of quantum mechanics comes in. Because as soon as you make a measurement, if you measure energy or position or momentum, you change the system. Without quantum mechanical tunneling like this, the sun wouldn't shine.
We have a sponsor for this episode of Apple Finch Pudding. But before I delve into this, I want to be very clear about what this sponsorship is being used for. This sponsorship is being used to support the podcast. This means buying subscriptions to software we need, maybe some editing, or buying some other material that will benefit the podcast. That being said, our sponsor for this episode is SciSummary. As researchers, we need to read a lot of papers, and more are being published every day. As a result, reading papers is becoming more or less a full-time job, leaving us virtually with no time to do our actual jobs, which is research. This is where SciSummary comes in. SciSummary provides you with an AI-based summary of the papers you provide. However, SciSummary is much more than just a summarizing tool. It lets you chat with your papers. You can ask questions, for example, like what material and methods are being used, but it can also provide you with insights as to what would be good avenues for future research based on the papers you provide. If you want to try out SciSummary for yourself, there's a link in the description below. If you use this link, you can have a 7-day free trial. However, if you want to go for a paying subscription, don't forget the code based on this podcast, which is AFP25. So AFP stands for Apple Finch Pudding 25, because you will get 25% off on your subscription. Go definitely check it out. See if it's something you like. If you like it, please go for it. But for now, let's go back to the show. Welcome to Apple Finch Pudding, your gateway into the world of science. Today's scientist is Philip Moriarty, a professor of physics at the University of Nottingham. His work focuses on nanoscience and quantum mechanics. Welcome, Philip.
Thanks, Jeroen. Great to be here. Thank you for the invitation to the podcast. I'm looking forward to, let's see, a wide-ranging discussion, perhaps.
Before we delve into that discussion, do you have a fun science fact for our listeners?
You did pre-warn me about this, I must say. So I've come up with 3. So hopefully one of these will resonate with your listeners. The first is, and I've got colleagues just down the corridor working on this problem. So you know the experiment, the demonstration we use to introduce electricity to kids, where we take a balloon and we rub it against our hair. Physicists still don't understand really how that works. It's a deep, dark secret. We know it's due to charge transfer, but is it electrons? Is it ions? What role does triboelectricity play? What role does humidity play? We still don't know, but we don't let the kids know that. We pretend that we know everything that's going on there. The second fun fact, and we did a video for 60 Symbols on this many years ago, is that watching paint dry at the microscopic level is absolutely fascinating. And the third fun fact, and your audience might have heard this one before, this is one I particularly like, is last year's Nobel Prize was awarded for attosecond spectroscopy, where we measure how electrons move essentially all the way down to the attosecond level, 10 to the minus 18 seconds. So it's difficult to get your head around that. And the fun fact that the Nobel Prize Committee put out in the promotional stuff about the Nobel Prize last year is that an attosecond is to 1 second as 1 second is to the lifetime of the universe, which I think is a really mind-expanding fact that I really, really like.
Yeah, that is really mind-blowing, actually.
Yes, absolutely. So that shows you the type of precision we can get down to now with measuring fast reactions, with measuring how quickly chemistry happens. And that's an exciting time to be in science.
Yeah, it sounds like it. Well, I actually also want to go back to your first fact, actually, because we always say it's just static electricity, but actually what's really going on on the small level, on the electron level, we don't know.
Yeah, we don't. So in fact, in many cases, for those types of static electricity, it's not even clear whether it's electrons that are being transferred or ions that are being transferred. And if it is ions, what role does water have to play? So what role does humidity have to play? And then it depends on if water is playing a role, how hydrophobic i.e. how much does the surface hate water, or how hydrophilic, how much does it love water is the surface. It's a huge area called triboelectricity. And it's fascinating. As I say, I've got colleagues down the corridor here who bounce little ball bearings off each other in little plastic containers and try and measure how the charge is conserved or not, how the charge is transferred. Let's be careful in choice of language here. How the charge is transferred and trying to control that. So yeah, it's really interesting. It's really fascinating.
And it's also so insane because everyone assumes, we know what's happening, but we don't.
Yeah. But we keep that quiet.
Okay. So we'll move away from that.
Indeed, yeah.
I'll start very broad. So we'll discuss quantum mechanics today. What is quantum mechanics?
Oh, wow. That's a nice, big, broad question. So I taught quantum mechanics to our second years for a number of years, to our second year undergraduate students. So quantum mechanics is the science of the ultra small. It's when we get down to the limit where we can no longer apply our intuition from classical physics, when we think smaller and smaller, or we work on smaller and smaller energy scales. And instead of treating particles as little billiard ball objects, what we have to do is take into account that when we get down to that level, particles start to exhibit wave characteristics. So in a nutshell, quantum physics, quantum mechanics is the science of the ultra small. In fleshing that out a little bit, it's all about reaching that limit where you've got to take the wave properties of matter into account.
Okay, so like you said, we don't assume anymore that particles are just billiard balls. They have waveforms as well. But,
precisely, yeah.
But what does that mean? They have a waveform.
So that's a really good, really great question. And actually, that's also, I would say, a very active area of research. So we have something in quantum mechanics called the wave function. This is a mathematical object that we can't observe. What we can observe, however, there's something that's very closely related to the wave function. It's essentially the square of the wave function. And that's called the probability density. So the wave that we're talking about is a probability wave. It's a bit like, if you had a map of a country and you overlay it on the top of that, where are the hot spots for crime? Where is it most likely to find crime? With quantum mechanics, what you have is a map, a probability density that tells you where's the greatest likelihood of finding a particle.
Is it then also like the orbitals and electron clouds that we're talking about?
That's exactly what we're talking about. So those orbitals, those electron clouds, the reason they're clouds and the reason they're fuzzy, and not like little solar systems writ small, is because of this probabilistic nature of quantum mechanics. That we talk about probabilities, we don't talk about definites. Although, it's a very intricate and very nuanced subject. There are certain circumstances under which you can talk about certainty in quantum mechanics, despite the fact that we've got the Heisenberg uncertainty principle, etc. This is something I tried a great deal to get across to the students, is that the popular understanding is that everything's fuzzy, everything's ghost-like, everything's ethereal. We don't really have complete certainty down there. In many cases, that's true, but in some cases, it's not true. Some cases, we can have 100% certainty in quantum mechanics.
You already touched upon the Heisenberg uncertainty principle. What is that exactly?
So there's a number of ways of describing that. So that's often seen to be, it's a nice way of drawing a link between classical physics and quantum physics. So the Heisenberg uncertainty principle is often seen to be this purely quantum effect, everything's uncertain, etc. How long have we got? Let me try and describe this. So because quantum physics is ultimately a physics of waves, in many respects, there are many analogies that you can draw and many parallels you can draw between quantum mechanics, quantum physics, and the physics of waves in the big bad world, including in particular music and sound waves, etc. Now, they're completely different types of waves, but an awful lot of the same things hold true. The Heisenberg uncertainty principle essentially tells us that if the more precision we have in measuring the position of a particle, the less precision we have in measuring its momentum, and vice versa. So if there's a precision in position, we'll call that delta x. I don't want to get too mathematical. If there's a precision in momentum, we'll call that delta p. The product of delta x times delta p is a constant. It's actually related to Planck's constant. So they have to trade off against each other. If that product is a constant, if you know delta x to higher precision, or delta x is smaller, then delta p has got to be larger. And everybody go, oh, wow, that's completely, we don't see any aspects of that in the world around us. Well, we do. So that's in terms of position and momentum. A parallel that we can draw is between frequency and time, and those are also important parameters and variables in quantum mechanics as well. But if I have a note that proceeds for a very, very long time, wave, just imagine it going on for, if I could take a deep, deep breath and whistle for 2 days or whatever, that has a very well-defined frequency. Really well-defined frequency. If, however, I go, so it's so short that you can't even hear it, you can barely distinguish the note itself, then you've got a great deal more uncertainty in what the frequency is. It's very well resolved in time. So very, very short in time, but you've got a massive degree of uncertainty in the frequency. That's the Heisenberg uncertainty. That's ultimately where the Heisenberg uncertainty principle comes from, because quantum mechanics is about waves. Music and sound is all about waves. You've got this fundamental mathematical relationship whereby if in one space you have a very accurate description of the wave, in the other space you don't. And that's not really to do with quantum mechanics. It's just the mathematics of waves. It all goes back to a wonderful French mathematician called Fourier. If you'll excuse the absolutely appalling French pronunciation. I did do French for high school, but it was the last year in which French was taught in Ireland, so that it was purely written. We never spoke it. We never listened to it. We just wrote it. So writing, I'm okay, and I can read French. You just heard how bad the pronunciation can be, though. So, but Fourier, all of this stems back to Fourier. In fact, there's the cosmologist whose name, John Barrow, who said that basically when you're a physicist, your very first approach to pretty much any problem is to try Fourier analysis, is to try transferring from, say, the time domain to the frequency domain. And we do that all the time in terms of, if we've got an EQ on an iPhone or we've got an EQ in a stereo, that's what you're doing. You're taking a complex load of waves that are interacting and you're saying, well, how do I make that more straightforward and simple? Well, let's look at frequency bands and let's control the frequency bands instead. So that translation from time to frequency, so from sort of the signal that's coming through the headphones to EQ, is essentially what we're doing with quantum mechanics when we translate from position to momentum. Though the link is not easy. It's not at all straightforward. It's not intuitive to think, oh, okay, I get that between frequency and time, therefore I can get that between position and momentum. Not least because momentum in wave language means something related to, but quite distinct from, I would say, in classical physics, the momentum of a ball. If I fling this at a wall, how do you represent that in terms of waves? And that's what a lot of undergraduates spend an awful lot of time getting to grips with in quantum mechanics courses.
In classical mechanics, I think you can link that also to the observer effect. Yeah, maybe you can explain better than I do.
Yeah, so the interesting thing is the observer effect is, so in the uncertainty principle, it's often said that the uncertainty principle comes about because the observer disturbs the system. That's not quite the case. That's in lots and lots of popular science texts, or at least it used to be in popular science books, and indeed even in a few textbooks. And indeed, you could make the argument that Heisenberg himself got it slightly awry. The uncertainty principle, so this position, momentum, uncertainty trade-off, is not, the observer effect is real, absolutely real, and it's a key part of quantum mechanics, but that's not what the uncertainty principle is. The uncertainty principle, take the observer away, forget about the observer, forget making any measurements. If you've got a particle in quantum mechanics that's confined like that, it has the observers, imagine there were no observers in the universe. If you've got a particle that's confined sharply to space, it will have just naturally a very wide spread of momentum. And that's ultimately because in quantum mechanics, we build up particles from a set of waves. I really need to get at the blackboard, which is over there. So if we want to have a particle that is really confined in space, we need waves that are wiggling very, very quickly. And if they're that are changing back and forth on a very short length scale. Just as going back to that example, if we want something that's very confined in time, we need a signal that's changing very quickly. So similarly, if you want a particle that's confined in space, you want waves that are wiggling very, very quickly in space. And if you add those up in just the right way, and this was Fourier's genius, lots and lots of sine waves of different frequencies, you add them on different phases, so where the peaks and troughs relate to each other, you add them up in just the right way, it's amazing. You can get a waveform that looks like an isolated particle. You just add up the waves, so they all cancel out over here, they all cancel out over here, and they all pile up in the middle. So that's really in terms of wave-particle duality, which is another aspect of quantum mechanics. When you think of it like that, it's natural. It's really natural that, we think of a particle as something localized, and then you think of waves, you drop a stone in a pond, you see the ripples, you don't think of that as localized. But if you add up those waves in the right way, you can get something that's localized. That's the uncertainty principle. It's fundamentally related to this relationship between position and momentum, or time and frequency. The observer effect is something different. And it's actually, for me, that's where the real weirdness of quantum mechanics comes in. Because as soon as you make a measurement, if you measure energy or position or momentum, you change the system. What we say is we collapse in traditional quantum mechanics language, you collapse the wave function. So you've got this sea of probability, or this cloud of probability is the best way of describing it, I think. Then you make a measurement, you go, the particle's here. And you say that you've collapsed this probability wave down to a value. Okay, that's the observer effect. And then the process starts anew again. So it starts off localized like that. And then if you follow it, you'll see that over time, the probability of finding that particle will spread out over space again. And then you measure it again, you find it in a different place. And then it'll spread out over time. That's the observer effect. That's the measurement problem, as it's known. And it's called the measurement problem for good reason, because we don't understand it, and it is a problem. We understand all the mathematics. We know how to make the calculations, but actually physically what's going on, another matter entirely. Okay.
Yeah,
that's about 3 months of quantum mechanics in 5 minutes. So apologies for
that. No, it was quite dense. We have learned a lot.
Maybe watch this at at half speed or something like that.
So, but we actually don't know why that waveform is collapsing.
That's a massive area. Yeah, that's a massive area of physics that we still don't understand. And it's remarkable. We can do the calculations. We can work out just what sort of probabilities we might expect. But ultimately, how is it that this probability wave collapses down is something that is still a very active area of quantum mechanics, which is great. Certainly for new people coming into the subject, instead of it just being a boring, here's the textbook, here's all the stuff we know. So it's a real opportunity to come along and explain to the rest of us dumbasses that have been trying to work it out for the last century, just what the hell is going on.
That wave-particle duality, that's also linked actually to the double slit experiment, right?
Absolutely, completely linked to the double slit experiment. It's a cliche to quote Richard Feynman, but having said that, he said very many incisive and perceptive things. And we, all physicists, are contractually obliged to mention Feynman at least once a day. So, yeah, he said that all the mystery of quantum mechanics is essentially in the double slit experiment, particularly because you take one particle at a time, one electron or one photon. There's a beautiful demonstration on YouTube where with an electron microscope, they have a double slit setup essentially established, and then they control the rate of electrons coming through. So you see the little pinpricks of light hitting the screen, and initially it just looks completely random, and then as it builds up in time, you start to see the bands due to the interference. So there's only one electron going through, and the only way to interpret that is somehow that electron is, if you'll excuse the language, interfering with itself. And forming the interference pattern. And yeah, that's one of the key aspects in terms, again, the weirdness of that relates to wave properties again, and relates to phase. In fact, an awful lot of the weirdness of quantum mechanics can be traced back to phase differences and how different peaks and troughs of waves, the relationship between them, did they pile up? Do the waves pile up in a certain place, increasing the probability, or do they cancel out somewhere, decreasing the probability? And yeah, getting a handle on phase is a tricky aspect of quantum mechanics.
And I can imagine for a lot of people that it's counterintuitive that particles have a waveform as well. Is there a way to actually combine classical physics and quantum mechanics?
Yeah, absolutely. So, and this is an experiment that is, what I'll do is I'll send you a link. All my stuff from the undergraduate course, I know it might be at slightly too high a level in terms of a general audience, but there are some introductory stuff. And one thing I focus on a lot, which is a key aspect of the research we do, is something called the scanning tunneling microscope. So scanning tunneling microscope is, in a nutshell, and we can talk about it maybe a little bit more later on, a sharp tip. You bring it in close to a surface. And when I say close, I mean within an atomic diameter or so, maybe a couple of atomic diameters. And classically, there's a gap. So the circuit is open, so you wouldn't get electrons flowing. But when you get down to distances, very small distances like this, then what can happen is electrons do this quantum mechanical effect, which is called tunneling. So even though there's a barrier, there's a gap there, classically you wouldn't measure current, but quantum mechanically you do. And we do this all the time. And in fact, that type of tunneling is what underpins, I'm looking for my disk drive, these type of USB sticks. Actually, that's how you get electrons on and off. So it's interesting that quantum mechanics is often seen to be incredibly esoteric, and some aspects of it are, but it's there in practical technology. And in fact, without quantum mechanical tunneling like this, the sun wouldn't shine either. So none of us would be here. So it crops up absolutely everywhere.
You can't drop it like that and not explain it.
Right. So tunneling is about, we know in terms of particles, if they've got the same charge, we know this from high school science, got the same charge, they're going to repel each other. Now, in the sun, in terms of fusion, we need to get two particles of the same charge to interact and fuse. Classically, if we take into account the amount of repulsion, they're never going to do that. So what we say is there's a big barrier for them to combine. But quantum mechanically, they can tunnel through that barrier. So they see a much lower barrier and they combine. Similarly, with the SCM tip, the electrons see a big barrier classically because there's a gap there, but quantum mechanically, they can go essentially straight through that barrier. It's like, I don't like using this analogy because we're not quantum mechanical particles, but it's like instead of, coming to the wall and stopping, it's like you walk straight through the wall. If we were just a quantum mechanical particle, and this doesn't just happen occasionally at the quantum mechanical level, it happens all the time at the quantum mechanical level. Got to point out, we are not quantum mechanical particles. It's why we don't walk through worlds, and it's also why when you walk through a doorway, you don't diffract. So part of you goes this way and part of you goes that way. So that's where tunneling plays a role in how the sun shines. But in terms of quantum mechanics and really the fundamentals of quantum mechanics, including your question about wave-particle duality, great thing about a scanning tunneling microscope is it can pick up and look at those probability waves. It can literally visualize and measure those probability waves. And in terms of links with classical physics, perhaps the most instructive link is with waves on a string. I'm a big metal fan. I'm a big rock fan. Actually, it's a good day today because Opeth, Swedish band, have released their new album today, which is just amazing. I was listening to it going into work. But so in terms of stringed instruments, you get, and some of you might remember this from your high school science as well, you get different resonances. You get different standing waves on a string. You can see that right down at the quantum level. It's the same idea. You have these probability waves that you can confine and trap in space. And there's a group in Germany who did a beautiful experiment a number of years back where they took individual atoms. So you can use this to image, but you can also use the tip to move atoms around. And they made little strings of atoms. And then they looked at how the electrons are distributed in those, and it's just like waves in a guitar string. You see that the probability density, and it's the same. You get node, antinode in the middle, then node, antinode, antinode, node, etc. Just as you have in high school physics for standing waves on a string. It's a beautiful experiment. So, although there's a lot about quantum mechanics that is esoteric and weird that we don't understand, there's a hell of a lot that we do understand, and there are lots of parallels with wave physics in the big bad world around us.
What is actually the most surprising fact in quantum physics, according to you?
I would say the measurement problem. So we've got the remarkable thing is, you put the observer to one side, you have a quantum system that's evolving, and then you make a measurement. And let's say we make a measurement of energy. We make a measurement of energy, we collapse the wave function. And this is what I meant about some things being 100% certain. If we now make a measurement of energy again, we get exactly the same result. If we measure energy again, we get exactly the same result. However, if we now measure position, we completely scramble the wave function. And if we make a measurement of energy, there's a much higher probability of getting a different value for energy. And if that's making your head explode, yeah, it makes all of our heads explode. We just don't get that. The measurement problem is core to quantum mechanics. And if we could understand just what the hell is going on there, and somehow also how the system knows that you measure an energy or position or momentum, which it does somehow weirdly seem to know somehow, because it behaves differently, it's a big, massive problem in quantum mechanics. But again, that makes it interesting.
Yeah, that's true. If you would already know it, I mean, that's it.
We'd be out of a job. Yeah.
Yeah.
Exactly. Yeah.
And is there also what is the most misunderstood concept of quantum mechanics for the general public?
I think the uncertainty principle, that distinction between the uncertainty principle and, well, there are a number of different things. Technically, I would say the uncertainty principle versus the measurement problem, those are distinct, but it's not surprising that those are scrambled because they are sort of, related in some ways. And even in the early days of quantum mechanics, they got very confused about that. In a much broader context, there's an awful lot of what's out there called quantum woo, for want of a better word, where people, there were quantum life coaches. Gwyneth Paltrow has all this bloody energy healing stuff with quantum healers, etc. And that's worrying because that really is, you can bleep this out later, but utter. And I think the core mistake that's made there is the idea that what's happening on the teensy tiny level scales up to the world around us. What they are essentially saying is that quantum mechanics plays a massive role in the classical world and dictates everything we do. And we are basically just big walking wave functions. We're not. And as I said, the experiment to do is just walk through the door close to you. You're not going to diffract. Doesn't matter how many times you do it, you're not going to diffract.
And your head might hurt after a while.
Yeah, exactly. So that I think that misinterpretation of quantum mechanics, whereby little things, subatomic particles and atoms and molecules, we are just interpreted as we behave exactly like they do. That's the most damaging aspect of the sort of public perception of quantum mechanics, I would say.
I also get what you're saying, because it's like, it's just fancy to say something is quantum. Like you have to even think on the quantum level. What does that even mean?
Exactly. Yeah, it's a wonderful buzzword. And the other thing as well is, there are these links that are drawn often between quantum and consciousness, for example. And the reasoning does seem to be, well, we don't fully understand quantum, we don't fully understand consciousness, therefore quantum and consciousness must somehow be connected. And that is not the most logical of reasoning. But yeah.
And actually, your work also focuses a lot on the nanoscale, on nanoscience. How is that connected to quantum mechanics?
Completely. So we can, the reason I'm so drawn to that wave picture is that we can see those electron waves on a surface. So when you go down, it's a real shame I can't take you down the lab, but you
I'll
take
have
a
to
metal.
come visit.
You please come visit. That'd be great. Or maybe next time we can do another one of these, and I'll take the camera down the lab, etc. But we can see those electron waves on surfaces. We can see them interfere. And a wonderful probably my favorite image in all of science over the 30 years I've been doing this, is something called the quantum Corral. And this is from a group in IBM, west coast of the US, led by a guy called Don Eigler. But the work was done by a guy called Mike Cromie. And they positioned, you may well have seen this image, they positioned 48 iron atoms using the tip of the STM, just painstakingly putting them in place. This was back in 1993, a long time ago. Painstakingly putting them in place. And then in the center of it, you see the rings of the electron density as the electron waves interfere. And the beautiful aspect of it is that the pattern you see of concentric rings is identical to patterns we see in the world around us all the time. In particular, if I don't know if you may have experienced this, you're sitting on a train, you've got a cup of coffee or a cup of tea in front of you. The train's sort of in the station and maybe it's getting ready to go and it's sort of gently resonating. And you look down in the cup of coffee or tea and you see a lot of concentric rings. Do you know what I'm talking about?
Yeah.
So that's due to standing waves. That's due to the fluid oscillating, hitting the walls, bouncing back, and forming what's called a standing wave pattern. The mathematical description of that is something called a Bessel function. If anybody's done undergraduate physics or engineering, they've probably left the room screaming now at the thought of Bessel functions. But the beautiful aspect is that, this cup of coffee system, imagine it's scaled down by a factor of about 100 million or so. And that's exactly the same pattern we see in these quantum corrals. So different system, different materials, different everything. In fact, and this is the beautiful aspect of it, the only thing that connects the coffee cup, room temperature, fluid, liquid in a cup, so many to millions of hundreds of millions of times larger, with the iron atoms on a copper surface, which was done at 4 degrees above absolute zero. The only thing that connects those two systems is the symmetry. The coffee cup is a circle, the quantum corral is a circle. Wave physics connects the two over this massive disparity of length scales. The boundary conditions, as physicists and mathematicians would put it, are exactly the same, and the symmetry is the same. Therefore, the solutions to the equations, the mathematical equations, are the same. It's just wonderful. That's why I do physics.
Yeah, it sounds so elegant, actually.
Yeah, it is. And, sometimes physicists kind of get a little bit carried away from that, and they sort of get into other areas and they go, well, is the symmetry the same here? Then everything must be the same. And it's not always like that. But in this particular case, it really is. You can have completely disparate systems on completely different length scales, and they give you the same output, as it were, because the maths is the same, the mathematical description is the same, and the boundary conditions are the same.
Does your work also relate to virtual particles?
Oh, now that's an interesting, not per se, that is a relevant question. Not per se, but virtual particles, for example, are related to something, for example, called the Casimir force, whereby if you have two plates, and because particles are popping in and out of existence all the time, there's a force that you can actually measure between those plates, which is due to the particles popping in and out of existence. We don't quite measure the Casimir force, but we measure a sort of related force, which is called the van der Waals force. So to answer your question, the short answer is no, with some caveats.
Actually, I also want to talk briefly about one of your papers. I have it open right here.
God, no.
If you don't like it, you can skip the
questions. No, it's fine. Go on, yeah.
The title of the paper is Self-Assembly and Tilling of a I can't even pronounce the title.
Prochiral, yeah.
Okay, I'll try again.
Yeah.
Self-assembly and tilling of prochiral hydrogen-bonded networks by isonicotinonic
acid. That is not the. So to be fair, that is not one of the titles that rolls off the tongue. I would in our defence, our most recent paper that's currently submitted and under review has the less tongue-twisting title of Timing the Escape of a Caged Electron. So we don't always write such awful bloody titles, and that's my fault. That awful mouthful of a title is my fault.
I would have been able to say that other title, actually. Sometimes scientists are really playing with it. There's also this title of a paper, Fantastic Yeasts and Where to Find Them.
Lovely. That's beautiful. Yeah. No, I think the problem is, so that paper is very technical, and it's in a molecular physics journal with a particular audience in mind. So it's a very technical paper. We could have, and we should have, by we, I mean me, should really have chopped that down. There's, we could spend a lot of time talking about this. I think there's scientific writing is often needlessly technical and needlessly dry. There's no reason why we have to write in the way we do. In recent years, it has become of increasing interest to blah, blah, blah. Almost, so many papers start off like that. And it's one of the reasons why I really took the opportunity to write a popular science book, because it forced me to write in a very different style. But anyway, you did have a question you said about the paper.
Yeah, well, one thing I want to add, I can almost guarantee if you don't write scientifically, you will get problems with reviewer 2 or something.
Absolutely, totally agree, yeah. In fact, though, we got the reviews back on this paper. It wasn't reviewer 2. In fact, the 3 reviewers were quite nice, but reviewer 2 in particular was very nice. So yeah, it was good. It's not always reviewer 2.
But about this paper, so self-assembly, that's something that also occurs actually in biology, but how does it occur here in nanoscience?
Great question. So we do sort of 2 separate strands. Oh, I could spend an awful lot of time talking about this. Thank you so much. We do 2 separate strands. So we use this scanning probe microscope tip to manipulate atoms and molecules. That's much more sort of engineering, brute force. Let's shove those atoms where we want them to go, and we've got a blueprint in mind. The other possibility is to just engineer the chemistry, or in your case, engineer the biology, so that the particles interact in the way we want them to interact. And self-assembly, in that case, we've looked at a lot of self-assembled systems. We essentially take a surface, a clean surface. We work in ultra-high vacuum a lot. And the reason we work in ultra-high vacuum a lot is because we don't want contaminants. We're working right down at the single atom level, single molecule level. And, if we were to work in air, all the gases would disturb the experiments. So we work in ultra-high vacuum, so big, shiny stainless steel systems, less shiny now. Some of them are 20 years old. And the pressure in there is comparable to that you get on the surface of the moon, about 13 orders of magnitude, 13 powers of 10 below atmospheric pressure. And that means instead of having to have surfaces corrupt in nanoseconds or whatever in air, we can work with them for weeks. So we create a surface. In that particular case, it was a silver surface, I believe. I'm trying to remember.
I think
it was
so,
a
yeah.
silver 110 surface. And so we clean that up in vacuum. And the way we do that is literally pummel ions off it. We call it sputter annealing. So you pummel it with ions, you heat it up, you pummel it, and then with not a huge amount of work, at least for silver, you get a nice atomically flat surface. You see the steps in the surface, you see electron scattering, etc., and you get it nicely clean. Then we have molecular evaporator, which is a very posh word for an oven. So we literally have a little crucible, little vial, and we wrap a filament around that. We pass a current through the filament. All of this is in vacuum. And then we sublime the molecules. So the molecules sublime as a molecular beam and hit the surface. And then they hit the surface, diffuse, and depending on the interactions, which in this case are largely hydrogen bond mediated, they come together in different patterns. And we're very interested, particularly in collaboration with our colleagues in chemistry just across the way and elsewhere in the UK and internationally, how do you control those interactions to get particular types of pattern? Because those patterns you form in terms of the molecules control how the orbitals of the molecules interact and overlap, and that controls, for example, how electrons will transport through this structure. And for example, can we control it so we get 1D assembly? Can you form molecular wires naturally? Doing that in metal surface is interesting. Perhaps not so useful, because if you have a molecular wire on a metal surface and you put a contact here and a contact here, the current's not going to want to flow through the wire. It's going to be shorted out. So you can assemble them. There's actually a big program of work in some groups working on self-assembly is if you've got these molecules formed as a wire and a metal and you need the metal to form the wire in the first place, can you lift it off and put it on another substrate? And that's actually quite tricky, but a number of groups are working on it. Not least the guy Meg Cromie I mentioned before. So yeah.
Is there an application for that? Is it like to construct nanomaterials that we can use in practice?
Yeah, it's ultimately in terms of the applications is can we have molecular electronics? And there are some aspects of that in terms of photovoltaics where we now are at the point where you do have wrappable electronics you can sort of fold up, or displays at least. So the question is really, can we push down? Can we functionalize the molecules so they have particular functions? So can we use individual molecules as diodes or transistors or even just resistors or whatever? And there's a whole huge area called molecular electronics, which focuses on trying to, I think it's going to be sometime before we supersede silicon and get rid of silicon. It's a vast, not just in terms of the technology, but just economically. Chip fabrication plants are billions of dollars. So that's a big economic investment there. But I think in terms of not superseding silicon, but integrating molecular electronics with silicon, I think there's still some way to go there.
In that case, like from nanomaterials, why do we need that self-assembly there?
Largely because it's cheaper. In principle, so if you can control, they draw this distinction between top down and bottom up. So with the top down approach, that's what we have now in terms of nanolithography, and it's amazing what the semiconductor industry can do. Features on chips now are just a few atoms across, and that's because they've pushed and pushed and pushed down in the limits. But they are starting to hit a brick wall, and Moore's law, this which you may have heard of, depending on who you speak to, has pretty much tailed off. Some people are more optimistic than others, but it's pretty much tailed off. And indeed, over the last 10 years, the focus hasn't really been on pushing more chips, more components onto a chip. It's been, how the hell do we deal with the waste energy? These things are heating up and melting down. How do we deal with that? That's really been the focus, which is distracted from the sort of Moore's law. How many features can we get in the chip? But that's a massive investment. It's very, very difficult. If you can do this from the bottom up by just dialing in the chemistry you want and getting the molecules to interact in the way you want, and just chuck them in a beaker, give it a slosh round and dump it out, or spin coat or whatever, that's a much cheaper, albeit more dirty approach, but that might be good enough for many applications.
So yeah, we're still on the nanoscale, quantum mechanics. We're still working there. Einstein famously said, God doesn't play dice. That makes people sometimes question quantum mechanics. Can you explain why he said that?
Because of the probabilistic stuff that we've talked about, this idea of you make a measurement again, you make a measurement again, you get different results, which seems completely bizarre from a classical physics perspective. If you set up your experiment, your controlled experiment, and your measurement is done in exactly the same way over and over again, if you're getting completely different results over and over again, you fecked up. You've done something wrong from a classical physics experiment. But from quantum, that's what happens. We have a probability distribution curve. And sometimes we get that, sometimes we get that value, sometimes we get that value, sometimes we get that value. It has a peak, so there is a preferred value that we get, but that doesn't mean that we can't get the other values. That's why Einstein, he had real difficulty with this probabilistic nature of quantum mechanics. But it's there. Every experiment we've done, the whole essence, the framework of quantum mechanics, mathematics, science, physics, measurement, all of it comes together. It's probabilistic. There's absolutely no way around that. And generally, when you say something as definitive as that, you're saying, well, maybe 50 years down the line, somebody will show. Maybe there is something deeper, but certainly at the level of where we're making measurements, that probabilistic aspect is absolutely as established as anything can be in science.
And that probability, is that always a normal distribution, or do you have weird distributions as well?
You also have weird distributions. You can have many, many, many different types of distribution. And in fact, that's a great question. What a great question. In fact, for those waves on a string type, the sort of nanoscale strings, that's very far from a normal distribution. In fact, you can see that immediately, because if you think about, so you've got your first resonance, which has got, I don't know if you can remember the standing waves on a string. I wish I could draw on a board. But if you can track my fingers across the first resonance, you've got a nothing at this side. Now, this is the end of the string. This is the other end of the string. And you've got a peak in the middle. Right. So in the quantum mechanics terms, that means you've got a strong probability. The highest probability is in the middle. However, for the second resonance, it comes up, node in the middle, goes down, and then out the other side. That means when you square that, you get something which goes rup with a node in the middle and rup on the other side. So that means you've got a high probability of finding it here and a high probability of finding it here. That's not a normal distribution.
That reminds me actually of really the quantiles, for example, for electrons that have discrete levels where they can occur.
That's exactly it. And in fact, I talked about that 1D sort of waves on a string approach that they made with their same. But in fact, you can, it's nice, we can bring this all together. With self-assembly, chemists have got very good, not just working in 2 dimensions, but in 3 dimensions. And they can form quantum dots, literally little chunks of matter where the electrons are confined in all 3 dimensions just through wet chemistry. There's a guy called Charles Murray in particular, Bawendi, Alivasatis. There was a Nobel Prize for this not so long ago. And you're absolutely right, in those little particles, that you have quantized energy levels, and in fact, often they're called superatoms. So they behave like a big atom, even though they contain thousands upon thousands of atoms. Because the electron waves are confined within this unit, it behaves like a superatom.
How do we envision a superatom? Because I'm still trying to wrap my head around it.
So the reason it's called a superatom is we have lots and lots and lots of atoms comprising one of these particles. So there might be 10,000 atoms in a particle. Let's say it looks like this. But the important thing is, because the size of the particle is comparable to, or indeed smaller than, the wavelength of the electrons that are contained within it, then what it does is it behaves like to trap and confine those electrons, just like an atom does, except it's much, 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 much bigger. Does that sort of make sense?
I think so. But and on what scale are we then talking?
Nanometers, few nanometers across. Anywhere from, they can control the size of these things from sub-nanometer, say, half a nanometer, 7/10 of a nanometer, all the way up to, tens of nanometers. And the great thing about that is by controlling the size, you change as you pointed out, you change the distribution of the energy levels. So essentially, if you can control the size of these things, you could think about building up a periodic table just on the basis of one element. So for gold, for example, you just could have a particle which is a nanometer, 2 nanometers, 3 nanometers, and the energy level spacing is changing as you change the size of the particle because you change the confinement.
That's really insane, actually.
It's amazing. Yeah, it's great. It's directly after this, another hour's time, I'm about to do another podcast with a guy called Professor Dave, who is a YouTube channel, who's great, and we're going to be talking about another YouTube communicator who basically keeps saying that science is dead, academia is dead, academia sucks, physics is dying, etc. And it's very frustrating because there's so much great stuff happening in science, and with what's happening across the Atlantic and the general pushback against science and expertise and universities, it's very frustrating to have this continual, academics are just shills for the establishment or whatever. So, but that's a whole other topic. Maybe we can talk about that another day.
Yeah, but that's insane, actually. Yeah. There's also a lot to think about on that side. But like you said, we'll leave that for another time. Before we close, do you have a take-home message for our listeners?
Another great and actually quite challenging question. So I'm often asked, I used to be what's called admissions tutor, which means I handled or oversaw applications from students for our courses. And, the question is, what course should I do? Should I keep a focus on, what the career opportunities are, et cetera, et cetera? And okay, those things are important, but I would say the most fundamental thing is do what you find interesting. Because if you do what you find interesting, or indeed, even better, do what you love, you will excel at that because you've got a drive there. And that's much better than trying to predict, well, what's my career going to be? What are my career earnings going to be at this point in the future? Do what you love. And the other point I would just say is don't believe everything you see on the internet. So, yeah.
Also not on podcasts.
Apart from this one. This one's
of course. That speaks for itself, I mean.
Great. Loved it. Thank you so much for inviting me on. It's been a real pleasure. Thank you for letting me, as I said, drone on for so long. I've enjoyed it.
It was a pleasure to talk to you. This was Apple Finch Pudding. I want to thank Philip Moriarty for the information. Let's meet again for the next episode of Apple Finch Pudding.